Modern AI can feel almost magical, right? It can master ancient board games, it can design brand new proteins. But there's this weird paradox at its core. That same genius AI can be surprisingly fragile. A tiny, unexpected change in its environment can make its performance just completely shatter. So today, we're going to dive into some really fascinating research that tackles this hidden flaw, showing us a clever way to build AI that's less brittle and a whole lot more dependable.
Okay, so to really get this, let's look at a super simple example from the paper that just nails the problem. On the left, you've got a standard AI. It's told to find the shortest path, and it does. It squeezes right between those obstacles. It's super efficient, but one tiny wobble and it's going to crash. Now, look at the AI on the right. It's playing a different game. It chooses a safer, wider path. Sure, it's not the absolute fastest route, but look at that huge margin for error. That's the whole idea right there. Are you aiming for peak performance or for robustness?
And that right there highlights this critical challenge that developers are facing. AI can be brittle. You can train an AI to be absolutely perfect in a simulation, but the second the real world doesn't match that simulation exactly, its performance can just fall off a cliff. We need AI that doesn't just work in theory, but actually works reliably out here in the real world. Which, of course, leads us to the big question. How do you actually teach an AI that a slightly lower scoring but much more stable strategy is the better choice? Well, to answer that, we kind of have to get inside the AI's head and understand how it sees its own performance. So imagine the AI is exploring what's called a reward landscape. Think of it like a giant invisible mountain range. Every single point in this landscape is a different strategy the AI could use. The higher the altitude, the better the reward, the higher its score. The AI's entire job is just to climb as high as it possibly can. But here's where it gets really, really interesting. It's not just about how high you can climb, it's about the shape of those high reward areas. On the left, you've got this sharp, pointy peak. Yeah, it's the absolute highest point, the perfect score, but it is so precarious. One tiny nudge, a little bit of unexpected friction, a motor that overshoots just a bit, and the AI goes tumbling all the way down into a low-reward valley. Now, on the right, you've got a wide plateau. It might be slightly lower than that tippy-top peak, but the AI can make small mistakes up there and still maintain a really high performance. It's stable. The way we normally train AI using algorithms like PPO, they're basically designed to find those sharp, narrow peaks. They are built to zero in on that one single best performing strategy. And you can see from this visualization from the paper, you end up with a very spiky landscape. The AI gets a fantastic score, but man, it is living on the edge. By contrast, the AI that was trained with this new method, the one that's looking for robustness, it finds a much flatter region of high reward. This is the goal. On this big, wide plateau, little stumbles and slight variations aren't a big deal. They don't lead to a catastrophic fall. The performance is consistently high, even if it's not that absolute theoretical maximum score. So how in the world do we get an AI to actually search for this flatness? The researchers used a really clever technique to shift its focus away from just finding the highest peak to finding the widest, most stable plateau. They used an algorithm called sharpness-aware minimization, or SAM. The way I like to think about it is that it makes the AI just a little bit paranoid. So at every step in its training, it looks for the worst possible little nudge to its settings, intentionally takes the tiny step in that bad direction, and then it learns how to improve from that slightly worse off position. By constantly practicing how to recover from these tiny, self-inflicted setbacks, the AI learns a strategy that isn't just good, it's resilient. As the original SAM paper puts it, the goal is to find parameters that are inherently robust. You're literally baking resilience right into the learning process. Okay, so that's the theory. It sounds good, right? But does it actually build a more reliable AI? To find out, the researchers ran a kind of digital gauntlet, pitting the standard AI against their new flatness-seeking version. They took these 3 virtual robots, a cheetah, a hopper, and a bipedal walker, and they trained them in a standard physics simulation. One version of each robot got trained the normal way, and the other got trained using that SAM method to find the flat plateaus. And then they started breaking things. First up, they introduced something called action noise. This is basically like making the robots a little bit clumsy. When the AI sends a command to a joint, a little bit of random error gets added in. So the movement isn't perfectly precise, which, is a lot more like the real world.
And wow, this table just brilliantly illustrates the difference. Let's look at the half cheetah, the standard PPO agent. It scored 4758 in a perfect world, but with those clumsy actions, its score absolutely collapsed to 1469. That's a 69% drop. Now, the SAM-trained agent, the one that seeks flatness, it actually started with a higher score and only dropped by 24%. It had learned a way to run that could handle a little bit of sloppiness.
This chart makes it totally crystal clear. You see that huge performance cliff for the standard agent, and then you see a much more graceful decline for the robust one. This is the value of finding that wide, flat plateau in action. All right, for the next challenge, they change the environment itself. What happens if the ground suddenly gets more slippery, or if the robot's body gets a little heavier? These are exactly the kinds of unpredictable changes a real-world robot has to deal with all the time. And again, the results were dramatic. For the Hopper robot, when they started messing with the ground friction, the standard agent's performance fell by an average of 77%. But the SAM agent's performance only dropped by 22%. It had learned a more general-purpose way to hop that wasn't just tied to one specific type of surface. So, what does all this mean? Let's zoom out a bit. Beyond all the charts and the simulations, why is this idea of seeking flatness so important? Well, it really signals a fundamental shift in how we should probably think about building AI. It's a move away from just chasing a perfect score in a perfect world. And it's a move toward building dependable systems that can maintain high performance even when our messy, unpredictable world throws it a curveball. The potential applications here are just enormous. We're talking about more reliable self-driving cars that can handle an unexpected patch of ice, factory robots that don't fail just because a part is a millimeter out of place, and safer robotic assistants in our homes that can deal with clutter or uneven floors. This is really the key to taking AI from the lab and putting it into our lives. So this research leaves us with a really powerful question. This isn't just about improving robots. It's a whole new lens for thinking about intelligence itself. If we can build AI that actually prefers stable, robust solutions over brittle, optimal ones, what other complex systems in finance or supply chains or even in scientific discovery could we make safer, more reliable, and ultimately a whole lot smarter?